All right, sweet. All right, welcome folks to today's Advanced Water Heating Initiative Connectivity Working Group call. Happy to have everyone here. Jeff, can I get you to read the compliance statement quick before we begin?
Sure. Antitrust compliance statement. The Advanced Water Heating Initiative, AWHI, is a member-supported collaborative of professionals from across the country. Excuse me. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and at any other AWHI meeting, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product and or accessory.
Thank you very much. All right, so our agenda today, go over some updates, and then we have an awesome presentation from Brian Woo-Shem on demonstrating simple price responsive controls, specifically for central heat pump water heaters. So excited to have that, and I think we have some other folks working pretty closely on that project as well, coincidentally. So we'll have some good discussion afterwards. We have some other upcoming webinars, such as decarbonizing commercial kitchens, if you're interested, near the end of May. A couple of new resources. I think we mentioned this last time, but there's the Earth Day fact sheet, and then also a cost compression report that was just put out that I helped work on. So definitely check those out. The cost compression one is focused on single-family home residential heat and water heater installations and kind of talking about the various factors that go into driving high install prices, as we're all pretty aware of. So if you're interested, you can click on the link in the slides, and I'll also put it in the chat. 1 second. I'll just gonna copy that and put it in the chat in a moment. And then we also are launching the connectivity tracker on our website. I think I've shared this before. It's just called like a meta-analysis. Basically, it's a repository of all the heat pump water heater load shifting studies that I'm aware of and that folks in this group have shared, which has been a good collaborative effort between this connectivity working group. And now it is being hosted on the Advanced Water Heating Initiative's connectivity webpage as well. So it's has a little summary to go with it and just makes it a bit easier to find. Yeah, Jeff?
Little point of fact, you've got an image there of a gas water heater, so we might want to swap that out.
That's a great point, and I will tell our comms team that they did that. I put together the tracker, but did not throw the picture on. So great catch, Jeff. That is pretty funny.
I mean, I will say that there will be flexible load management for gas water heaters in the future as well. So it's not impossible. But
absolutely. No, good to know, but I will make that correction. It's pretty funny. And then we also have a heat pump water heater photo repository that we're working on just to kind of have more high quality photos that'll be publicly shareable. So hopefully a helpful resource for a bunch of folks just to have more kind of available stock images for all the reporting work we all do. And I think there's a lot of photos that get reused and repurposed a lot. So just to get some more heat and water heater photos out there is always great, especially for marketing and whatnot. So yeah, you can email my colleague Joe at newbuildings.org if you have any good photos of your own heat and water heater or from pilot projects or programs. That would be great. So yeah, then if we have anybody who has not been here before, I'd love for you to come on camera and just give a quick intro, who you are, where you work, kind of what your involvement in heat pump water heater connectivity is. It's like it might all be returning faces. No worries. Sweet. Okay, well, I'm going to pass it over to Jeff for a brief update.
Yeah, thanks, Noah. What I'm helping to do right now with AWHI is do a little fundraising. As many of you know, there have been some changes in Washington, D.C., and so some funding is a little bit tight. We currently only have one OEM sponsor who is signed up for this, but I would encourage anybody else, both an OEM and or utilities, who are looking to help support this great cause. I'm volunteering to help raise this extra funds to cover this. And I sound a little bit like the local radio station doing a promotion here. But if you have any interest in sponsoring, even at a modest level, please reach out to me or Joe Wachunas, and we can get you signed up. It does come with some benefits, such as some consulting time, some access to some metadata, as well as some microdata, all anonymized, but it would allow you to get some insights for your particular interests. So reach out to me. I'll put my name in the chat. And Jackson's question, we're trying to raise about $150,000. DOE funding has fallen short, as well as with EPA now potentially shutting down, we have less amplification, so we're going to need more work. AWHI could be sort of the glue that holds us together for the next stretch of life. And so being a former NIA person, I would say this is a great opportunity for people to step up and participate. So Skycentrics is the first OEM to commit to this, but I'm reaching out to others, and I'd like to get some feedback and insights as to what you need and how it will be more palatable. Thank you, Noah.
Thanks a ton, Jeff. Really appreciate that. Awesome. Well, without further ado, I will turn it over to Brian. Thanks a ton for being on this call, Brian. I'm excited to see how you share your work. And I'll stop sharing screen so you can share.
Awesome. So just give me a moment to get this.
Yeah, no rush.
I'm usually a Zoom person, so it takes me a few seconds to figure out where everything is.
So on this share screen button, I think the best thing that works is if you go to the PowerPoint Live. That's usually pretty helpful because then you can see your own screen and move without and still being able to look at your slides and like notes and everything. So because there's the share screen and then lower down is PowerPoint Live.
Let's see.
Brian, while you're loading up, I noticed, Noah, that we have the next meeting is today. Do you have one in June or July?
Oh, funny. Yes. Oh, that's actually a great point. Thank you so much, Jeff. In June, we will not have a meeting because we're going to be directing folks to instead come to the all stakeholder meeting. And I will throw the date on there. I think you should all have the invite, but I think that is in late June. So I'm going to pull that up right now. That is our all stakeholder. I had it on my calendar recently. Yes, it is Wednesday the 18th from 9 to 10:30 a.m. So in lieu of this meeting, we'll be directing all the working groups to come to the all stakeholder meeting. And the AWHI all stakeholder meeting was quarterly before, but now it's moving to only biannual. So it'll kind of for 2 months of the year in June and December, it'll replace the other working group meetings, and we'll kind of have some representation for all the different working groups there. So definitely check that out. All right, Brian, floor is yours. Thanks so much.
Great. Hello, everyone. I am Brian Woo-Shem, a technology researcher at Lawrence Berkeley National Lab. My work primarily focuses on load shifting controls for devices including pool pumps, water heaters, and thermal energy storage, with smaller projects on heat pump water heater training and M&V of thermal energy storage systems. So this presentation is about the development and field demonstration of simplified price-responsive controls to minimize electricity costs of central heat pump water heaters under dynamic pricing. So this is a significantly expanded version of a presentation I gave at the ACEEE Hot Water Forum back in March. We have 2 additional tests and a lot of additional analysis to show. So in the future, electricity rates may become more dynamic, changing hourly or even more frequently than that. Some utility companies are introducing hourly flex price pilot programs with prices that vary each day, such as these from PG&E's program. With dynamic pricing, optimizing the schedules manually for devices becomes much less practical, and our solution is to have automated load shifting to minimize costs. And the goal of our work at Lawrence Berkeley National Lab is to develop an adaptable algorithm that can determine a near optimal schedule from the prices and a few measurable or calculated site parameters. Highly dynamic pricing reflects the cost to supply electricity at a given time. And for part of this field test, we use an example typical day, highly dynamic price for winter and summer, where it's unfortunately the same price every day, but it's still a dynamic price in the sense that it has that kind of shape, shown in the red and blue lines here. And then we also tested real highly dynamic prices from the PG&E Flex Price pilot program. So California has set a target to have 7 gigawatts of load flexibility by 2030, with the goal of improving grid reliability and resiliency while making electricity more affordable by reducing the costs during peak load times. This project is funded by the California Energy Commission's Electric Program Investment Charge through CalFlex Hub, a program of studies to identify, evaluate, develop, and demonstrate demand flexibility technologies that are not yet on the market, and help the state meet our 7 gigawatts goal. The overall CalFlex Hub portfolio includes 90 test sites with projects in HVAC, EV charging, battery energy storage, thermal energy storage, smart thermostats, smart panels, home energy management systems, pool pumps, heat pump water heaters, and heat pumps across single, multifamily, residential, commercial, and campus projects. The EasyShift algorithm used in this study was initially created under the Store for Build project, a multi-lab collaboration to develop and deploy thermal energy storage. EasyShift was originally created for hydronic heating systems with air-to-water heat pumps, but was designed to be intuitive and adaptable to any system with energy storage. Since the tanks in central heat pump water heater systems provide thermal storage, we adapted and validated EasyShift for this application. The approach for providing load shifting attempts to find the ideal balance between non-flexible controls that are currently present in most devices and are only able to satisfy demand and equipment constraints, and then our most advanced controls, such as model predictive control, that can provide optimal results but have limited adoption because they're just more challenging and expensive to deploy. So this project leverages EasyShift, a simplified MPC, or it could be considered an advanced rule-based algorithm, designed to be simple to deploy while providing near optimal results. And for this project specifically, as electricity costs have increased, building managers who retrofit buildings to have central heat pump water heaters are not consistently seeing savings on their energy bills. So the goal is to see if we can use the load shifting controls for central heat pump water heaters to help bring those costs down. The performance of the algorithm was demonstrated through field testing at 2 affordable senior housing sites in San Francisco, California. These are operated by the Tenderloin Neighborhood Development Corporation. They have graciously allowed us to run tests on their equipment and encourage our work to reduce operating costs for the properties, which they can reinvest to better serve their tenants. This presentation will focus on results from the larger site where we have done the most testing. The sites are primarily studio apartments with 115 to 140 residents. These are century-old buildings that were retrofitted in the past few years to have a central heat pump water heater system. This builds off of learning from load shifting studies performed by others to reduce costs under time of use rates, especially those done by Ask Energy and supported by Ecotope at these same field sites. Some of you may be familiar with this, but I'll go through a little bit of how these systems work. So the central heat pump water heater systems have 2 heat pumps that provide hot water to a series of tanks. The storage tanks may hold hot or cold water, and we can adjust the state of charge by changing the ratio of hot water and cold water. So the storage tanks feed into the swing tank, which goes to a thermostatic mixing valve and delivers hot water to the occupants. Recirculation then returns back into the swing tank. When we want to run the system and maximize storage, load up mode activates the heat pumps to increase the amount of stored hot water, and then to avoid using energy during a period, bottom image, the system stages the heat pumps such that only one runs at a time generally, and it allows the amount of hot water to decrease to a minimum level and prevents the swing tank from running. And the CTA 2045 signals configured at the site allow us to switch between 4 modes. They are listed here from most energy saving to producing the most hot water. From top to bottom, critical peak mode minimizes the energy usage by setting the tanks to a low state of charge and staging the heat pumps that only one activates at a time most of the time and locking out the swing tank. Please note that although it is called critical peak, it can be used on a regular basis in response to prices as we'll describe in the following sections. It should really just be considered an alternate shed mode. Shed is a mild energy saving mode that sets the tanks to a low state of charge, but keeps the heat pumps and swing tank active when needed, which ensures there will be hot water. Normal mode is the typical operation, which has a large deadband for heat pump operation cycles that are many hours long, and load up mode charges the tanks by running the heat pumps as much as possible.
Hey, Brian, quick clarifying question. Jackson asked, what is the total capacity of the tanks in gallons?
I'd have to check, but I think it's on the order of 1,000 gallons. I could look that up
Awesome.
afterwards.
Yeah, that sounds right for a central system. Sweet. Thank you.
Of course. So the difference between shed and critical peak modes is that critical peak cannot be used at certain times without sending cold water to the building. So I'll try to explain how that works. So assuming that you have relatively high domestic hot water draw, the swing tank will stay warm because there's higher temperature water flowing in from the heat pumps and storage tanks into the swing tank as water is removed from the recirculation loop. So under these conditions, critical peak can be used and the swing tank can be disabled. However, if your domestic hot water draw is too low, very little water enters the swing tank from the heat pumps and storage tanks, so the same loop of water is just circulating between the swing tank and recirculation loop. And then over time, the thermal loss in the building recirculation will cause this water to cool, and if the swing tank resistance heating is not active, the occupants get cold water. When we do not run any load shifting, the system is in normal mode all the time by default. So the large deadband range causes the heat pumps to typically have a single long operating cycle, and the system typically starts the morning with a high state of charge, and then as occupants use hot water, the state of charge decreases. Around early afternoon, the amount of hot water decreases enough to hit the deadband, and the heat pumps activate, and then they stay on through the entire evening peak consumption period and into the night until the tank state of charge is at the upper deadband. So this pattern of lagging behind the domestic hot water draw, especially in an evening peaking building, and running all at once, is really not ideal under California electricity pricing, where the peak demand on the grid and peak prices occur in the late afternoon and evening, which incidentally is when these heat pumps typically end up running the most. So now I will walk through how the easy shift algorithm that we've developed optimizes the heat pump operation. So we need several inputs. First is storage capacity. That's just a constant system parameter based on tank size and temperature sensor locations. So it's essentially the range of most hot water versus least hot water that we can put in there. Then we look at the heat pump maximum output and domestic hot water load or draw. This is a recent average based on data collected at the site and then converted to kilowatt hours. We then need the hourly electricity prices at the site and weather forecasts for outdoor air temperature, which is used to predict coefficient of performance based either on manufacturer specifications or, when possible, a model based on the historical data from the site. So these two items are combined to get the cost to heat the water during each hour. So that's the green line represents the cost to produce 1 kilowatt hour of heat or thermal energy in a given hour. So to create a schedule for the next 24 hours, EasyShift then goes through each hour or looks forward through each hour, increasing the heat pump water heater operation at the least expensive remaining time until the target thermal energy storage is within the allowable ranges, both the maximum and minimum, for the entire period, and it satisfies the hot water load for the entire time. Note, I'll emphasize that this image is generating a schedule for a given horizon. This is still happening all at hour 0. It is looking forward based on these predictions to create the schedule. So that and then at the end, this is the schedule that it produces. A few things to notice, in hours 10 through 12 here, it's obeying the maximum storage limit by only limiting how much it can run. And then in hours 19 through 23, it avoids running out of hot water by using just the minimum energy needed to satisfy the load, but does not use any more since it determines it is not cost effective to run during that time unless it has to. I'm getting a lot of background noise. Maybe check if people are muted, please.
Yeah, I can do. I think I hear somebody coughing. I'll make sure folks are muted. Thanks, Brian.
So then once we have this target storage level and heat pump water heater operation, we need to convert that to EcoPort signals, at least for this field test. So first we look at the range of thermal energy to be expected for each mode, and it's essentially which deadband range corresponds to that amount of thermal energy storage. And we can simply assign each hour to the mode that matches the target storage for the end of that hour, because that's what we want it to do during that hour. So we want to set it to that mode. Then we adjust to make sure that it matches the expected heat pump behavior, because when the heat pump is operating at max capacity, we want to force the mode to load up regardless of what state of charge it should be in. And then if the heat pump is supposed to be off, the mode should be either critical peak or shed. Next, to determine whether to use shed or critical peak, we look at the expected draw. And previous testing found that when the draw is relatively low, recirculation losses dominate and the swing tank needs to operate where the temperature drops below set point, as I kind of showed in a diagram before. And so the dark red line indicates the threshold for high versus low draw and was determined experimentally for the site. We use shed mode, which is less efficient, but allows for the swing tank usage to prevent issues when the draw is below that line. And then critical peak, which is more efficient when the draw is high. So here we can compare the electricity consumption throughout the average day of 1 week of testing with Easy Shift, as well as 3 baseline weeks that are in the light blue color. And then I've highlighted the difference in electricity consumption between these two cases. So yellow or / orange color, depending on how it shows up on your screen, indicates that more electricity was used during an hour, and the size of the shaded area indicates how much, and then teal indicates that less electricity consumption occurred during an hour. And we see that under this winter pricing scenario, the total draw was similar, and Easy Shift reduced the cost by about 31%. It increased the system CO peak slightly, and it maintained the proper set point nearly all of the time. The temperature dropped very briefly during low drop periods under critical peak in the first couple of days of the test, which is why this reliability is not 100%. So we increased the minimum draw threshold even higher between the critical peak and shed modes to prevent issues. And then we had perfect reliability after that point. We then tested a summer highly dynamic price, which is characterized by a single large peak price in the late afternoon and evening. So the algorithm responds by using load up starting at the low price in the relatively early morning, and then continuing to keep the state at a high state of charge through the afternoon. And then it uses the storage to avoid the highest prices and keeps the tank at the lower state of charge through the night. And this plot here, similar to the other one, compares the average electricity consumption between Easy Shift and the baseline weeks, but for the summer pricing profile. And again, yellow-orange indicates more energy used, and teal indicates less electricity used. Overall, this test reduced the cost by 42% and increased the efficiency slightly by running the heat pumps during the late morning and early afternoon when heat pump COP is higher. We're seeing good reliability here as well. And then PG&E hourly flex pricing is a pilot program that customers can enroll in with a variable rate based on wholesale prices forecasted up to a week ahead and finalized the day ahead. So the larger plot here shows a sample of different days and the average price for the field sites since the hourly flex pricing for this location became available on January 2nd of this year. Note that prices are higher in the summer and fall, and we unfortunately do not have data for those yet, and prices can vary by much more at other locations, but since the field sites are in an area with a relatively stable grid connection, they have not shown extreme high price periods that we have seen at a few other locations. So we've been going through the pricing at a bunch of different locations just to kind of look at what we see to get a sense of what the potential is, and these sites have a relatively stable price profile. Some other sites we saw have pretty large variation occasionally. So prices at the site for the days that we tested are shown here. And in the spring, electricity costs are generally low, especially low between 10 a.m. and 4 p.m. when solar production is plentiful. And the morning and evening peaks are less pronounced because heating and cooling demands are low during the relatively temperate weather. Instead, we just see generally elevated cost overnight relative to midday. For the hourly flex prices, the price varies each day, so I cannot show a single average plot like we did for the other price profiles. So instead, I've shown 2 example days here to hopefully give an idea of how this algorithm is performing. So the first day, April 6th, that's the left half of this plot, is an extended period of low or negative prices through midday, and the price peaks overnight. And then the second day has more pronounced peaks in the early morning and evening around 5 to 7 a.m. here, and then evening around 6 p.m. So the prices are lowest again in the early afternoon. And the resulting electricity consumption is shown in dark blue, and I've included the light blue as well as a comparison point. So for the most part, the easy shift algorithm is able to take advantage of those extremely low price periods or even free or negative price electricity periods during the late morning and early afternoon. And under this pricing, the easy shift control showed 36% cost savings, primarily from shifting load away from peak price times, but also by improving the efficiency by about 9%. This is largely because the prices were so drastically lower midday, it caused that most of the operation to occur when outdoor air temperatures were higher, and thus the coefficient performance is higher. We encountered some challenges with the system, especially when trying to run load shifting. So if the system remains in load up when the tanks are already at the maximum state of charge, sometimes the temperature of the inlet water to the heat pumps increases due to warm water being pushed out of the storage tanks. This decreases efficiency since R744 heat pumps perform best with large temperature differences. One possible explanation suggested by a subject matter expert is that the storage tanks have both series and parallel connections, which several blocks of 3 tanks then connected in series. So if the last 3 tanks in the system are not balanced perfectly, one of them may be pushing hot water through the heat pumps while the others will still be cold. However, this hypothesis cannot be verified because it's prohibitively expensive to install additional temperature sensors in all of the tanks to identify what's going on with the stratification. Another challenge is the system configuration allows for reducing, but not eliminating load during the peak price periods. The tanks are large enough to provide a few hours of hot water during the daytime hours, but are not large enough to avoid operation the entire high price periods in this test. And also the system is configured such that even after a long load up period, when switching to critical peak, one heat pump will usually remain running the entire time if there's even a moderate level of draw during that time. This test was performed using open loop controls, which pre-schedule a few days ahead using forecasts for weather and prices. This is really a workaround for equipment without real-time communication, and is less efficient because it cannot adapt to changing conditions. This forces us to schedule very conservatively for the most difficult scenario to ensure that hot water demands are already met. Hot water demands are always met, and it reduces opportunities for savings. You may also have noticed that there were a couple cases where we did not have hot water demands met, and that was because we were trying to figure out the thresholds ahead of time for this open loop. So ideally, we would use a closed loop receding horizon that updates each time step based on current measurements. This requires frequent communication to and from the heat pump water heater, or running easy shift locally on the system with prices and weather sent regularly. This is more efficient because it can adjust to the current demand and performance, and it can have more aggressive load shifting on days when draw and temperature conditions are more favorable to load shifting. Open loop control led to some issues that reduced performance during these tests. So on the left plot, the inlet temperature to the heat pump water heater in hour 3 here spikes during a long load up period, and then that decreases the efficiency and coefficient of performance. And then effective closed loop controls would detect an issue like this and shut off the heat pumps, even though it's still in load up mode. On the right, a plot from one of the first days of the test shows that low draw during a critical peak period led to the supply temperature dropping below the set point. And this is where we had to increase the threshold and just blanket set shed mode during those hours so that even if this occurred again, the swing tank would still be active. Finally, as you may have experienced in daily life, weather forecasts are really less reliable when further into the future. And again, the solution used in these tests was to schedule extremely cautiously to ensure that hot water demands were met on the most challenging days, which decreases savings at other times. For the flex price tests, the price forecasts are also imperfect. This reduces savings as the schedule is optimized around the forecasts, but the site would pay the actual rate. So a closed loop control in this case, again, would eliminate the issue. 3 major areas for our future work are first, implementing closed loop controls, which would integrate directly with the manufacturer's controls or through frequent communication with an external controller. We'd also explore other communication protocols such as OpenADR3 or others that are being developed could be used for this purpose. Second is performing long-term field demonstrations to optimize around available rates such as the dynamic pricing pilot programs and measure ideally the effectiveness of these over an entire range of price profiles that would occur for, say, an entire year, calendar year, Whereas it's hard to make a definitive statement on whether they save costs under just under just over a week of testing. We could also adapt the algorithm to reduce demand charges under current time of use rates. And third, we'd like to apply EasyShift to take a site's electric rates and draw profile, and then be used as a sizing tool to compare the first cost of different equipment sizes and determine the optimal tank and heat pump size to minimize the lifetime cost. For example, it could determine if adding more storage to increase the shed duration at these field sites would be economically viable or not. Overall, our work demonstrates the ability to schedule and optimize central heat pump water heater operation automatically. In field tests, we were able to reduce operating costs by 31 to 42%, even with a non-ideal open-loop control setup on imperfect field sites. The EasyShift algorithm also has potential as a sizing tool. It provides automated load shifting with relatively easy commissioning and setup, and these features lead to achievable cost savings for building operators and grid reliability benefits for utility companies. So thank you all for your attention, and I hope this was interesting and informative. I'll welcome any questions or suggestions from you all.
Thanks a ton, Brian. That was an awesome performance. An awesome presentation. Yeah, it was really great. A lot of good questions coming in. One was, did the algorithm arrive at a scenario where resistive heating is dispatched? And then kind of following up on that, especially if it's during when prices are in negative, would that dispatch the resistive heating?
Sorry, I missed a couple words in there. Can you?
No problem. Yeah. So, did the algorithm arrive at a scenario where resistive heating was dispatched, or if the price is negative, especially, did the algorithm dispatch resistive heating just because of those highly dynamic prices?
Yes. Let me show this slide again. So we would ideally like to do that, but we do not have individual control over the components. We only have these modes, which are designed to, rightly so, around energy efficiency as much as possible, because negative pricing is kind of an unusual case to see, and just we were able to test during that just to kind of see what it does. So we tweaked the algorithm a little bit to at least use shed mode instead of critical peak if the price is negative or zero, and try to use load up as much as possible, but it cannot, especially during times of higher draw. Generally the system will just controls internally will automatically avoid running the swing tank. So unfortunately, we did not have a way to induce swing tank operation intentionally, even though we thought about that and we wanted to do that.
Understood. Great answer. Peter?
Yeah, I just wanted to add a quick little addition to Brian's great response there. We've talked a little bit with manufacturers about integrating this control algorithm directly into their products. And if we were to go in that route, and we did have a manufacturing partner, presumably we'd be able to directly control the resistance elements and the heat pumps, so we could make it happen at that time.
Sweet. And did manufacturers seem interested in the collaboration?
We've only talked to one, but sample size of 100% of manufacturers are interested.
Awesome. I mean, yeah, seemed like great controls and relatively straightforward to explain too. So that's great. And then another question from Daniel: what is the rationale for the quick succession of load up to normal? What is the rationale for the quick succession of load up to normal to shed events in the summer pricing scenario when prices are low throughout?
Yeah, that's a good question, and one that we spent a little time looking at as well. So the algorithm is trying to minimize costs, and it does not really differentiate between like a 0.01 cent cost saving versus like a many dollars cost saving. It's just looking at anything that saves costs. So in this case, if you look carefully, I don't know how big it shows up on your screen, the price in hour 3 is the lowest, hour 4 is second lowest, and hour 5 is a little higher than those two. So it's purposely trying to avoid, it's basically trying to do a shed during hour 5 to avoid operation then. And that's
fascinating.
The succession between those. So it's looking at, the algorithm just kind of sees this as slightly more expensive, slightly less expensive. Let's avoid the more expensive time.
Yeah, interesting. Are you going to shift that around at all, considering it's still like to adjust it for like relative pricing, since even that slight bump in hour 5 is so much less than the critical peak around hours, what, like 16 through 21 roughly?
Well, that would be something to consider, but what's going on here is the algorithm's kind of trying to run. It's trying to charge the tanks as much as possible during the lowest cost hours, and the lowest cost hours of the day, according to the once you factor in the heat, or lowest cost to heat the water, would be hour 3, 6, 7, 8, and then after that, the next best is 9. I know this because I was staring at it. And so and the other hours from say 10 to 16, it's already hit the maximum storage. It's just simply keeping the tanks at the at that level by keeping it in load up in order to maintain that level of storage, because its main priority is to avoid this big peak between hours 16 through 20. But then in hour 20 or so, it's at the minimum storage, but it sees that the price is going down continually for the next hours. So because it sees the price is going down, it sees, oh, the next hour is cheaper, let's just keep it at the minimum level until the next hour. And that's what it's doing.
And remind me, I think you might have mentioned this, but what is the set point temperature for your load up?
Set point temperature for the load up. I think it's around, well, the system was around 100. Let's see, the heat pumps are always outputting, I think, around 160 or so Fahrenheit. The set point, the thermostat, though, is set to some other number, maybe 130-ish, somewhere in the tank, because we're trying to avoid sending hot water into the heat pumps.
Yes,
so it's got some other deadband somewhere in the tank that's somewhere in between.
Awesome. Okay, yeah, thanks so much. So no, that's very hot storage. So definitely helping you coast through your critical peak period. Wonderful. Well, other folks are welcome to just come on camera or unmute themselves and ask questions too. I know I think we hit the ones in the chat. Yeah, Ben?
Yeah, hey, sorry, I don't know what's up with my camera. I promise I'm a real human being and not a I don't know what that is. Brian, this is very, very cool. And you were actually talking about wanting to, as you progress the development of the Easy Shift algorithm, of directly integrating with more bits of hardware, with more potentially more data around the site to be able to do this load shift even better. This is something I'd love to chat with you about after, because we make an OEM agnostic load controller that I think you might it might be useful for your tests. I'd love to make some available for you.
Great. Glad to hear that. We're always looking for partnerships, especially with different manufacturers. You're probably all familiar with this, but the labs, our goal is to support businesses and support the ability to bring these technologies to market. So I have the slide with my contact info here. So if you jot that down, and just probably best you should reach out to us afterwards. We'd be happy to set up with a meeting with you sometime.
Awesome. I'll reach out. Thank you.
I see some chat messages about questions about slides showing up or not showing up. Let me try showing.
I was seeing the graphics. I think the animation just might have not been happening, but it was no big deal. Like, it was still pretty clear what was going on. Might have just been a Teams issue.
Okay. Yeah, other questions, comments?
Yeah, we'll give folks another sec here if there's any thoughts percolating. But yeah, super impressive savings from the algorithm and everything. And just fingers crossed that these highly dynamic prices will be implemented before too long on the grid, so we can use this, have these real life savings, right?
Oh, they are, because the hourly flex price pilot, you could actually in most of PG&E service area, you can actually sign up for those.
Really?
Now.
Oh, amazing.
So we actually mentioned this to the site, but we're not sure if it makes sense to do. But or it's really up to them to decide. We just kind of explained, okay, this exists. it showed savings here, but we also don't have right now. It's a little bit laborious to set up these tests just because we don't have the entire scheduler system automated right now. So we need to find budget and resources to figure out how to automate it for them if we wanted to do that.
Yeah, okay, great to know. Thanks for that context. DC?
Yeah, I had one final question. I know you mentioned that you saw one of the heat pumps was running consistently in the critical peak mode, but not in the shed mode. Could you speak a little more about that? That seemed curious to me.
Sorry, I may have been confusing. Or the way I said it may have been confusing. It's that typically I'd see one heat pump running during the critical peak just to keep up with demand, essentially. And in shed mode, I'd typically see, because shed mode is not staged. Let me go back to the slide that shows the different modes. And while I'm trying to figure that out, so the difference is shed mode turns on both heat pumps at once. Critical peak stages them such that one heat pump comes on initially, and only if the deadband hits an even lower deadband will it activate the second heat pump. So typically what happens under critical peak is it pretty quickly hits that first deadband, and then the heat pump, just one heat pump goes on. Under shed mode, I'm more likely to see two heat pumps go on, and then because it heated some water, then they both go off kind of behavior.
Gotcha, thanks.
Understood. Sweet. And this might be more of a future endeavor, but do you take demand charges into account at all using the algorithm?
That's something we've looked into. We'd like to do that, and we're actually talking to some people about some projects to do that, because these sites actually these sites actually do pay demand charges under their current time of use rate. And we think it's something that can be done. We do not currently have that in the algorithm right now, though.
Awesome. Awesome. Yeah, thanks. Great. Well, if there aren't more questions, folks can, looks like you have your contact info, Brian. So folks can always follow up. This meeting is also being recorded, so it'll be posted on YouTube if you want to review any parts of it. And we'll also set up the slides next week once the video is posted. But yeah, thanks for coming, y'all. As I mentioned before, instead of the meeting next month, we'll be having our all stakeholders meeting on the 18th at 9 until 10:30 Pacific time. And I did post that link in the chat if folks aren't already signed up for the all stakeholder meeting. And then we will resume our normal session for July. So yeah, if I will send follow-up slides and more information on the next discussion as well. But yeah, thanks so much for coming, y'all. Again, really great presentation, Brian, and thanks for the engagement, folks. We will see you at the all stakeholder meeting, hopefully. Cheers.
Thanks, everyone.
Yeah, thank you.